So here we have a system that involves a spacecraft and a planet. And this spacecraft is on a planet that has no atmosphere, so we can negate air resistance in this case. There's no air resistance, and we're going to assume that there's no actions being done to the spacecraft that's going to keep energy from being conserved. So this system gives us an initial position of the spacecraft and the final position. It gives us the velocities at those points and the distances. So we have here the mass of Jango, the radius of Jango, we have the mass of the spacecraft, we have the initial and final velocities, which are both 0 of the spacecraft, and we have the final position from the center of the planet for the spacecraft. So the radius here is going to be the distance, the initial distance from the center of Jango to the center of the spacecraft. Here we want to find the spring constant K, so we can know the stiffness of the spring that launches the spacecraft into the air. So, important things to remember are that here in this case we're going to have a system that will be conserved energy. So we have the initial energy equals the final energy plus the change in energy. But in this case we're going to forget about this because we have the same energy in the initial point as well as the final point of this problem. So we're going to use the initial potential energy plus the initial kinetic energy plus the potential energy of the spring initially to equal the potential energy of gravity at the end, the final position, plus the kinetic energy of the final position plus the final potential energy of the spring, which is going to be 0, given that the spring is on the planet and it's in space. Alright, so for the potential energy of gravity initially at rest on the planet, we're going to use the constant G to get us our result with the mass of the planet times the mass of the spacecraft all multiplied together divided by the radius of the planet, which is going to be our distance from the center of Jango to the center of the spacecraft. Our kinetic energy is going to be 0 because we have an initial velocity of 0. Our potential energy for our spring is going to initially be 1/2 times the constant K times the stretch of the spring. In this case it's compressed 15 meters, so that's going to be squared. And we don't know that yet because we do not know K. So this is our variable we're looking for here, this problem. And then the final potential energy of gravity is going to be the new position from the center of the planet, Jango, which is going to be 4.6 times e to the 8th meters. We're going to get this. And so our final kinetic energy is going to also be 0 because we have a final velocity of 0 meters per second. And our final potential energy for our spring will also be 0 because we have no stretch in the spring being compressed. So, once we find these, go ahead and stick them into our equations. We have a 0 initial kinetic energy. We have our spring potential energy initially, and we have our initial potential energy from gravity equal to our final potential energy of gravity plus the final kinetic energy, which is 0, plus the final potential energy of the spring, which is also 0. As we solve for K, we find K to be very weak, and it is 3.09 times 10 to the negative 4th Newton meters. This is because the gravity of this planet is so small, it took very little stiffness of the spring to launch this spacecraft into space.